Hi again, everyone. Welcome back to our course in college algebra. Dr. Tom McNamara here, continuing to talk about polynomials. In the last video, we had discussed a procedure for figuring out the zeros of a polynomial. And let me go here and review the steps. It was first, we make a list of possible zeros, then we test to see if anything on that list actually is a zero. And we did the test using synthetic division. And if we do find a zero, it's very important that we factor. Okay, so I want to do an extra example in this video of the importance of doing this, okay, because it's going to be the case here that some of the zeros don't show up on the list. Okay. So let's start with the list. So the rational zeros test tells me that if something is a zero of this thing, if something is a rational number zero, then the numerator has to be a divisor of 12 and the denominator has to be a divisor of 1. Okay, so the possibilities for the numerator is anything that divides 12. Anything that divides 12 is a possible numerator for our rational zeros. The possibilities for our denominator are anything that divides the lead coefficient, which in this case is 1. Okay, so my numerator, I actually got tons of possibilities. 1, 2, 3, 4, 6, and 12 itself. 1, 2, 3, 4, 6, 12. That's 6 possible numerators. For my denominator, well, not so many. For my denominator, it's just plus or minus 1. Okay, so possible rational zeros. 1, 2. I better go down a line there. I'm going to run out of room, I think. 1, 2, 3, 4, 6, and 12. I do have to account for the possibility of those either being positive or negative. Okay, so let's go ahead and do some tests. We're going to test these with synthetic division. Notice I put a placeholder 0 right there. You see how our polynomial goes from the x cubed term, skips the x squared term, and goes right to the x term? There is no x squared. When you're doing your synthetic division setup, you have to put the consecutive powers here in your coefficients. So if the x squared term is missing, you need a placeholder 0 like we have right here. If you don't put that in there, it's going to screw up your answer. So that drops down, 1, multiply, add, multiply, add, multiply, add. Okay, so we're testing -1. We did not get a remainder of 0. That means -1 is not a 0 of my polynomial. Or sorry, that means 1 is not a 0 of my polynomial. All right, so if the first thing we try doesn't work, we go to the next thing on the list. In fact, let's go to 2. 1, 0, -10, -12. Skip a line here. Drop down. 1, multiply, add, multiply gives me 4, add gives me -6, multiply gives me -12. Shoot. I thought that was going to work. Why didn't you work? Okay. So that didn't work either. Let's keep going down the list. Let's try some more things. Let's try -2. Okay, what are my coefficients? 1, 0, -10, -12. Drop down, 1, multiply, -2, add, -2, multiply, 4, 2 negatives. -6, multiply, +12, because the product of 2 negatives, 0. Finally, that took longer than the previous examples, right? In the previous couple of examples, I had worked it out beforehand and figured out which one was a 0, so the first thing I tried in the video worked. But here, I had to try a couple things, and that happens, right? It's a list of possible zeros. It happens that 1 and 2 were not actual zeros. -2 is a 0. Okay, so we have found a 0, which means we have found a factor. So, one of the factors is x plus 2, okay? Remainder of 0, that means I have a factor. If you know a 0, then x minus that thing is the factor. So x minus -2 is our factor. And of course, x minus -2 simplifies to x plus 2. What's the other factor? The other factor is x squared minus 2x minus 6. Now we're working on finding the zeros of this thing. So it's a quadratic. Okay, we know how to do this. Now I think about it, I try factoring it, I'm looking for factors of -6. 1, 2, 3, 6. I need a pair of those that add up to give me -2. Two numbers have to multiply together to give me -6, but add together to give me -2. None of those do the job. None of the things I listed do the job. So I'm going to have to resort to the quadratic formula. Quadratic formula tells me that, and of course we know what it is, but I'll write it down just to make sure we're all on the same page. ax squared plus bx plus c equals 0. The quadratic formula says if that's true, then x can be found by doing this. -b plus or minus square root of b squared minus 4ac, whole thing over 2a. In this case, b is -2, so -b is 2, plus or minus the square root of b squared. -2 squared is +4. Remember, when you square something, you always get a positive. Minus 4 times a, which is 1, times c, which is -6. Whole thing over 2 times 1. Let's do some arithmetic here. Multiplication before addition, right? Order of operations. So -4 times -6 is +24. So this is a 28 right there. Whole thing over 2. How can I simplify radical 28? Well, radical 28 is, 28 is 4 times 7. So 2 radical 7. Whole thing over 2. Everything has a factor of 2 on top. Factor out the 2, cancel with the 2 downstairs. 1 plus or minus radical 7. Okie dokie artichoke. So, the zeros are x equals -2. We found that one with synthetic division. The other two zeros are x equals 1 plus radical 7 and x equals 1 minus radical 7. Notice those did not appear on the list. Those are irrational zeros. The list that we make comes from the Rational Zeros Theorem. It gives us a list of rational numbers, aka fractions, that could be zeros. But your polynomial could have irrational zeros. The only way to find those is to make sure you're factoring and then working on a simpler problem at the next step. Okay, because if you kept going down that list, you're not going to find any more zeros. The only zero on that list that was an actual zero was -2. Okay, none of the remaining numbers on that list would be zeros. The other two zeros are right there. And we got them by applying the quadratic formula. Okay, now you'll notice between the previous videos and this one, when I'm doing this, I only need one successful synthetic division to start getting the rest of the zeros. If you have a higher degree polynomial, then you may need more than one synthetic division, but you've got to keep breaking that polynomial down at every step. So this is a good example to show you why you need this factoring. Okay, if you didn't figure out this factoring from the result of your synthetic division, you won't find all three zeros of this polynomial.